In this module, we will discuss the three modes of cumuliform convection in the tropics, separated by their vertical extent into the troposphere. There are three modes of cumuliform convection observed in the tropics. The plot on the left depicts distributions of the number of convective cells, seen as a function of their height. First, there are shallow cumulus clouds. They are generally 0 to 3 kilometers in depth and are numerous. Shallow convection is pretty much ubiquitous through the tropical oceans, except in regions that are very dry. Cumulus congestus are taller, more laterally expansive clouds that often consist of multiple updrafts that are part of the same cloud complex. They are non-precipitating clouds with a modal height around 5 kilometers, which is approximately the 0 degree sea level in the tropics. Some non-precipitating clouds extend higher into the atmosphere, and some cumulonimbus clouds are the same height as a typical congestus cloud. Deep cumulonimbus clouds can extend up to the tropopause. On the right are the heights of the tops of 20 dBz radar echoes in convection over the Indian Ocean. 20 dBz does not correspond to cloud top height, but it does still show a bimodal distribution. One mode peaks at 2 to 3 kilometers, and a second mode peaks at 5 to 6 kilometers. These correspond to the congestus and the deep cumulonimbus modes. Because the sensitivity of the TRIM radar was about 17 dBz, neither shallow convection nor the tops of the deeper convection could be seen. So here you're seeing two of the three modes. Shallow convection, like that shown in the picture, is common in the tropics, and especially where sea surface temperatures are warm. Shallow moist convection can easily be triggered by turbulent motions in a warm, moist boundary layer, and distributes moist static energy vertically through the boundary layer, and exchanges more efficiently with the lower free troposphere than entrainment processes at the top of the boundary layer can alone. In locations where trade winds are present, these are sometimes called trade cumuli, and are topped by a strong inversion through which the clouds cannot easily penetrate. A minimum in tropical cloudiness tends to occur between about 600 and 800 millibars. The figure shown currently illustrates the frequency of cloudiness as a function of height estimated from sounding data, in which a cloud was assumed if relative humidity in the sounding exceeded 93%. Based on this metric, clouds are present 4 to 6% of the time below 800 millibars, and more frequently above 600 millibars, but only about 2% of the time between 600 and 800 millibars. Over long periods of time, these percentages also reflect the typical long-term aerial coverage of cloudiness at these levels. The clouds below 800 millibars represent commonly occurring shallow convection, and increased cloudiness above 600 millibars probably corresponds to lateral expansion of clouds as altocumulus or altostratus in locations where moisture has recently been entrained into the environment by cumuliform convection. Clearly, though, something seems to prevent many shallow convective elements from getting higher than 800 millibars. This appears to happen because a climatological layer of negative environmental buoyancy is present above the boundary layer, at least over tropical oceans. These figures shown were calculated from two different numerical cloud-permitting simulations of tropical convection over the Indian Ocean. Blue regions indicate where the mean buoyancy in the model domain was negative. The simplified expression used to compute buoyancy is shown at bottom and is sensitive to the difference in temperature, T star, pressure, and mixing ratio between the environment and clouds. In general, the temperatures of updrafts in this 700 to 850 millibar layer are actually cooler than the surrounding environment by a small amount, less than 1 degree C. This causes updrafts in this layer, on average, to decelerate. Only the most intense updrafts can penetrate this layer to become moderately deep congestus-like convection, and so a mode of convection that exists only within the boundary layer and part of the negatively buoyant layer exists. Congestus convection, as shown here, tends to be more laterally expansive and deeper than the shallow boundary layer convection we just discussed. This type of convection transports moisture to higher altitudes and is also very sensitive to the vertical profile of moisture in the lower free troposphere. Its presence over several days can progressively moisten the environment, which reduces the dilution of moisture in convective updrafts that subsequently form and reduces the negative buoyancy imparted upon these updrafts through the process of entrainment. The modal height of such clouds is at about the level of the 0°C contour. This is because, locally, freezing releases latent heat and stabilizes the atmosphere near the 0°C level. Updrafts that are only marginally strong enough to penetrate the lower free troposphere given their initial velocity out of the boundary layer, combined with entrainment of subsaturated air along the path through the free troposphere, are not able to penetrate this additional stable layer. Such clouds often diverge moisture into the environment near this stable layer, and thin altostratus or altocumulus cloud layers are often present as a result. Convection with updraft velocity large enough to penetrate both the stable layer above the boundary layer and the stable layer at the 0°C level can grow into deep convection, which frequently precipitates. This rarely occurs in dry environments because entrainment of the dry air in the lower free troposphere causes deceleration of updrafts. Deep convection can penetrate the tropopause and reach as high as 20 kilometers in the tropics. It is responsible for most tropical rainfall, although this rain generally occurs over relatively short periods of time. Deep convection also grows laterally into sometimes expansive mesoscale convective systems, which we will discuss in detail in a future lecture series. The current figure illustrates satellite-derived precipitation throughout the tropics, subtropics, and mid-latitudes. Most of the surface area on Earth does not experience rainfall at a given moment in time, although satellite imagery would reveal that shallow convection is present over much larger regions than where precipitation occurs. In this figure, which is a snapshot in time, most of the colors seen in the tropics correspond with the locations of deep convection. You can see a lot here over the warm pool. It is in the deep convection where vertical motions are upward. Therefore, the transport of energy and moisture from the boundary layer to the middle and upper troposphere occurs almost exclusively through the deep convection. While shallow convection is present in many other locations, the majority of the free troposphere experiences gentle descent or subsidence. This diagram illustrates some idealized clouds in white with vertical motion vectors shown in blue. The red lines indicate arbitrary pressure or height levels. Most of the atmosphere is cloud-free. If this isn't already intuitive to you, it will be if you pay attention to cloud populations wherever you are for long periods of time. Outside of the clouds, air slowly descends, as seen by these light blue vectors outside the clouds. The descent inside the clouds is much faster relative to the gentle descent outside the clouds. Divergence occurs at the top of the convection, these green arrows that appear, causing lateral distribution of moisture and energy, and convergence occurs near the base of the convection, in the boundary layer, and perhaps also in the low free troposphere. The lengths of the green arrows near cloud base in this diagram are intentionally shorter than those at the tops of the clouds to indicate that the mass flux into cloud base should be the same as the mass flux out of the cloud top, approximately. Remember, the density of air decreases exponentially with height. In the regions of descent, the atmosphere warms adiabatically, and it becomes slowly drier through vertical advection. As an atmospheric column dries, it becomes more transparent to terrestrial radiation emitted from below. Emission of long-wave radiation to space causes cooling of the atmosphere. Drying the atmosphere increases the radiative cooling that happens in the troposphere because fewer absorption interactions occur. Inside the clouds, rising motion causes adiabatic cooling. However, the release of latent heat caused by phase changes of water balances much of the cooling. This balance between diabatic and adiabatic heating and cooling, both in and out of the clouds, is known as radiative-convective equilibrium. On long timescales, we can say that the tropical atmosphere is in radiative-convective equilibrium. However, the atmosphere is not in radiative-convective equilibrium at all places all the time. It is deviations from this equilibrium state that drive moist convection. Alterations to the large-scale subsidence outside clouds can make the environment more or less favorable for convection by altering static stability. Consider the two plots shown here. On the left is a hypothetical change in large-scale vertical motion associated with some disturbance. It indicates that the disturbance causes a decrease in downward motion in the clear air environment, and the biggest decrease occurs around 500 millibars. The right-hand panel shows the changes in adiabatic heating rate in blue and radiative heating rate in red associated with this change in vertical motion shown at left. Reducing the subsidence moistens the atmosphere, therefore the radiative heating increases. At the same time, adiabatic heating decreases because you have less downward motion. The sum of the two causes the lapse rate in the lower troposphere, seen in black here, to increase, making the environment more conducive for convection to penetrate the stable layer present above the boundary layer. As convection develops, large-scale mean vertical motion may become upward, but this only happens because convection is already occurring, stabilizing the environment back toward an equilibrium state. In other words, upward motion that occurs in data sets should only be used to indicate that convection is happening, not that the environment is becoming conducive for convection. This simultaneous discussion of large-scale and cloud-scale processes we've had thus far has been a little convoluted, so in the next module, we'll discuss the difference and show a method for quantifying convective and radiative processes at various scales and modeling our observational data sets that divide the atmosphere into discrete spatial intervals.